Thank you. It's good to be here. Thanks for having me. I'll reciprocate what Nico said. It's great to see a large group of people here in a wonderful location interested in security. So I'll talk a little bit about myself, if this is working. Perhaps not. Well, it is switching locally. Let's see that. Oh, there we go. All right. Boom, boom. So, for those of you unfamiliar with my background, much like Miko, I've taken the approach of essentially doing the same thing repeatedly over and over and over again until people consider me an expert. So, I spent about 25 years looking at Windows internals, publishing books on Windows internals, doing blogs, starting companies, and spending basically every living second of my life almost doing Windows and still being alive. So now I'm considered the Windows expert. Interestingly, though, a lesser known part of my career is that I actually worked at Apple for quite some time as well. I was actually so sick of Windows, I decided to go work on something else that wasn't Windows. So I worked for about 5 years on the core platform team at Apple, doing the creation of the first iPhone, which we called the Purple 2 project. So that's a part of my life I don't talk much about because of Apple's well-known secrecy, but it gave me the opportunity to have all of this Windows knowledge through reverse engineering while writing code on a very different platform, right? Not only Mac OS being different from Windows, but also the ARM architecture being different from x86. Which has been fun for me to see how today's ARM64 architecture is actually increasingly similar to Intel and AMD's x64 architecture. The differences between the two are getting smaller and smaller. So with that said, I've got this interesting kind of platform knowledge base of how Windows works, as well as how Mac OS and iOS works, and I've also done some Linux work on the side. And I do believe in history, and I do believe in reading and understanding how things in the past were built. So I have some big knowledge of VMS and CPM, and I use DOS. So I try to think of myself not only as a Windows person, but as a kind of an operating system platform person, both as a developer and architect, as well as a reverse engineer and malware researcher. And in my younger days, rootkit developer, but never gave anyone any of my floppy disks. I spent a big part of my career, the last, up until 2 years ago, 10 years at CrowdStrike, where I was one of the founding employees there, which became today, I think, one of the largest cybersecurity companies in the world, certainly the largest EDR and XDR vendor in the world. But 2 years ago, I left to go work for the public sector. So I'm now working for the Canadian government for what's called the Communications Security Establishment. You can think of that as Canada's NSA or GCHQ, essentially. And I'm director of platform operations there, as well as research. And I will not be talking about any of that. So I also kind of have this interesting background of spending 10 years in the private sector, finding APT, and then eventually becoming the APT. So I kind of retired from public speaking 2019. I kind of gave a talk at OffensiveCon, a keynote, talking a little bit about kind of my life and how I got to where I got and some advice for people stepping into the industry. But from time to time, I think when there's interesting opportunities to speak to new audiences, to new places, I come out of retirement a little bit and meet some new faces. And I'm really glad I came here because I think Miko and I have known of each other and probably read each other's books and blogs for a decade, but I've never actually met in person. So that's at least one thing I'll get out of here, if not more. So why do I think that the next 5 years are going to be interesting as it comes to platform security and more especially Windows security, but a lot of what I'm going to be talking about here applies to kind of all platforms. Well, a big reason for that is that security of the operating system is really, really getting good. I mean, Nico talked a little bit about how browser security has improved a lot. OS level platform security has also improved quite a bit. Things that were being discussed in the 80s or 90s academically are now actually being implemented in major operating systems. Big reason for that is obviously the continuous push through cybersecurity, where we're seeing more and more the impact of attacks. Another big reason is security always comes at the cost of performance, right? You can't have a solution that is perfectly performant and perfectly secure. It just doesn't work that way. But as we start having, gigabytes and gigabytes of RAM, or terabytes in some cases, as we start having dozens of cores on consumer computer systems, you can go buy an AMD Threadripper, $1,000, and you've got 128 cores. You can buy a cheap $200 Intel processor, and it already has 16 cores. We still don't write software today that necessarily is using all of those cores all the time. This gives a lot more margin to security products to consume some of that CPU usage, to consume some of that memory, and therefore the bargain between security and performance kind of changes, because we can harm performance a little bit without the user noticing. Right? If I'm using 2 out of your 16 cores, but you're not actively playing a computer game while compiling some software and video encoding something in 8K, you're probably not going to notice that. So what are some things that we're seeing in operating systems today? One of them is strong signing, right? So with Windows, kernel drivers have to be signed since Windows Vista. Linux also now has signed kernel modules. Mac OS has been enforcing signatures. So the kernel, the privileged part of the operating system, has had signatures for quite a while. But what we're now seeing operating systems move toward is user mode application signing as well. Mac OS has the notarization process, right, through which if you want to run applications on Mac OS, they have to be signed or notarized by Apple. There are still ways to kind of bypass that. You can, as a user, manually run an application that's unsigned, but enterprises can enforce that mode, right? And in that mode, you can only run signed or blessed by Apple applications. Well, Windows 11 now has that as well. Microsoft calls it Smart App Control. And with Smart App Control, again, every application has to be signed by a CA that Microsoft trusts, or it has to be reputationalized to the level that Microsoft has seen this binary run on enough Windows computers, and nothing is flagged as malicious. So hopefully it's not a very successful botnet, because reputationalization is always interesting. But it is something Microsoft kind of trusts due to its prevalence on systems. So you also have hypervisor-based code integrity, which is also on by default in Windows 11 on modern hardware, and that takes code signing in the kernel and protects it by the hypervisor. So on modern clean installs of modern operating systems, your applications are increasingly subject to this requirement of being signed. And of course, it's not that a virus writer couldn't, or an APT developer couldn't sign their application, but signing does give you some interesting benefits in terms of being able to revoke certificates, being able to fingerprint and timestamp things, and it does raise the bar significantly. For things that are unsigned, we're seeing a move toward increased sandbox and containerization technologies. To take another Microsoft example, Windows 11 now has Win32 app isolation, which lets you run legacy applications that might be unsigned, that might be vulnerable in a VM, essentially, or in a sandbox, depending on your settings, minimizing the impact they could have on the system. Right? If the app is vulnerable and old, but it runs in a sandbox or it runs in a VM, there's not much that it can do on your host. So code signing is one aspect. Another aspect is the increase in memory safety. Right? Most, I would say, vulnerabilities today are still due to memory corruption or memory safety issues. How do we address that? Well, one of the things I'm sure you've heard a lot about is Rust. Right? Rust is kind of being talked about a little bit, sometimes too much, as a panacea for solving memory safety issues. It is not a panacea, no solution ever is, but it does significantly, once again, raise the cost of successful memory safety, because it makes writing code a process that's a little bit more cerebral for developers, where you make it a little bit more clear as to what your interactions are between memory and how that memory is being accessed. It makes it harder for you to have accesses to memory that are kind of not authorized or not understood by you. So it's not that writing code in Rust automatically makes it bug-free, but it makes you think a little bit more, and it removes or eliminates certain types of bug classes. So Microsoft has started, for example, to write certain components in Rust now, or to rewrite certain components in Rust. So parts of font rendering in Windows, which is owned by something called DirectWrite, it's under the DirectX umbrella. DirectWrite font parsing is now written in Rust. The Windows Window Manager, a well-known vulnerable component that actually runs in a kernel, now has pieces of code related to what's called region management written in Rust as well. Regions are basically, frame buffer areas. It's a lot of computation around boundaries, right? And then where you're drawing pixels and not drawing pixels. A lot of potentials to go out of bounds. Rust makes it harder to do that. And so they've rewritten some code there in Rust as well. And they've promised to continue investing in Rust, whether it's taking the Windows Networking Protocol, SMB, and moving it from the kernel in user space and writing in Rust, or the print spooler and writing that in Rust, right? They have a roadmap for components to move in that direction. Credentials are another aspect of attacks today, right? Attacks are not always necessarily going to exploit some memory corruption vulnerability. In many cases, they're just going to steal your credentials. How do we make stealing credentials harder? Well, since Windows 8.1, Microsoft has supported something called LSA Protected Process Lite, or PPL, that makes it harder, but not impossible, for your credentials to be stolen on a Windows machine by an attacker. That's now by default on in Windows 11. The second thing is Credential Guard. Credential Guard takes your domain credentials, your Kerberos ticket, and other single sign-on information, and it protects that information by the hypervisor. Now, with the hypervisor there, it essentially means that without some sort of tier 1 hypervisor vulnerability, your Kerberos ticket is now, and your single sign-on materials are now protected in such a way that past the hash attacks essentially no longer work. So even if your machine gets compromised, even if the attacker gets full kernel level execution, they can still not get your credential information from memory. Now, they can still install a keylogger, they can still trick you into revealing the password, but they cannot steal the password anymore from memory. And of course, the biggest and best solution is to not have a password at all anymore. So Microsoft has strongly moved toward biometric authentication and hypervisor protected biometric authentication, where, for example, you're using your finger or your face, just like on a phone, to authenticate. And that cryptographic material is, again, protected by the hypervisor. And even in Windows 11, the drivers themselves that are capturing your face or capturing your fingerprint, they run in the hypervisor, or they're protected by the hypervisor as well. That means that your host OS physically doesn't see the hardware that's capturing your face anymore. Much in a similar vein to Apple's iOS secure element, in which when you're doing a Face ID transaction, right, an iOS app, or even a compromised XNU kernel on iOS cannot see the facial recognition data. It's handled by a separate chip. Microsoft in Windows 11 does a very similar thing with the hypervisor technology. And so, of course, removing passwords means that there's nothing in memory for an attacker to steal to begin with, right? You have essentially some cryptographic token stored in a TPM, protected by the hypervisor, and that's what's used to authenticate accesses. And so there's this whole adminless, passwordless movement that Microsoft is trying to make. Another big area of security attacks has to do with persistence. Once I get on your box, I want to persist and remain on your box. That is very hard to do, for example, on a phone, because phones have signed partitions, read-only partitions, and environments that make it really hard for you to write code that's going to survive a reboot that's not designed, that's not installed by the user. Xbox is another example where where the game data goes and where the game gets installed is very different from other partitions. macOS has a feature called rootless, right? Even though you're running as root on macOS, there's some partitions you can't touch. Now, Windows has kind of been lagging behind on this, but they did build a feature a while ago called state separation and Windows storage spaces that was meant for Windows 10X. Now, Windows 10X never shipped commercially, but parts of Windows 10X technology remain. Some of them actually exist on Xbox. Some of them existed on Windows Phone when that was a thing. And there are rumors that Windows 12, aka Hudson Valley, will bring storage spaces and state separation to Windows desktop systems. In that environment, and you can still find images of Windows 10X online, your C drive is no longer this one partition with everything on it. You instead have an OS level drive that can only be updated by the Microsoft signed OS updater, which runs outside of the OS. And then you have your software drive, and that partition can only be updated by signed legitimate software installers while the OS is running. And then you have your user data drive, and that has all of your user documents and programs. It's encrypted with a user key, And your programs cannot access your data partition without the right entitlements and the right permissions. That makes it a lot harder for me to create malware as an executable because executables cannot persist in a data partition. Executables can persist in a software partition, but they have to be installed in a specific way. So my ability to kind of remain on the system gets harder. And of course, with environments like Windows 365 boot, where you're actually running a fresh image of Azure every time, and you're not even really booting your computer, if I persist on your computer, it doesn't really matter because you're booting off from Azure. And persisting in Azure, of course, is a unicorn. Not saying it's impossible, but that type of ephemeral-based operating system makes it even harder to do that. And finally, have the extra exploits themselves, the exploits that try to attack memory safety, that try to get your credentials, that try to persist. Those exploits use a number of vulnerabilities, a number of techniques to get code execution or to get memory corruption. And I won't go over the entire laundry list here, other than to say that Microsoft is constantly investing in hardware and software security mitigations, which basically mean that it's harder for exploits to actually get to their goal, right? To kind of steal a Zen quote, if there's a vulnerability in a software program, but it's impossible to exploit it, is there really a vulnerability there, right? Yes, there is. You can point in code and say, hey, that string copy is overriding a buffer that's not validated. But if you can't do anything other than maybe crash the program, who cares at the end, right? And so all of those mitigation that Microsoft is adding, that hardware vendors are adding, essentially make it so that even if there is a bug, well, we don't really care anymore, right? It's not going to be something that can be exploited to gain an advantage on a system. At worst, it'll be a denial of service attack. And in a cloud microservice environment where the microservice can be restarted in 1 microsecond, sure, there's a DOS and the user just had to press F5 to refresh the page for things to work on. So Windows, but other operating systems as well, are getting increasingly tougher to exploit, to attack, to persist, and to get meaningful data out of. Now, at the hardware level, things are getting harder as well, right? So there's a lot of talk about UEFI, EFI, firmware attacks. Those are also being mitigated. Microsoft and Apple have worked very closely with Intel, AMD, ARM, and BIOS manufacturers to really, for the first time in I'd say 30 years, mitigate some attacks that you could do back in the 80s. There's something called SMM, or System Management Mode, inside of every Windows PC or even Linux PC. That's often called Ring -1 or Ring -2. There are a number of innovations that make SMM a safer environment, up to on what Microsoft calls secured core computers, essentially running SMM in user mode under a hypervisor and mitigating anything that malicious SMM code could do. So that entire class of vulnerability that you might hear about is slowly dying. Then there's physical attacks against computers. Microsoft used to say, if someone has physical access to your computer, it's not your computer anymore. Now, unclear if they still believe or don't believe that anymore as far as Windows is concerned, but on Xbox, for example, and on Windows Phone, there was and there is a hardware boundary around even physical access. And on modern Windows computers, you're seeing the same thing with technologies like Secure Boot, DRTM, Measured Boot, which either make your computer impossible to tamper, or at the very least what Microsoft calls tamper evident, in a sense that I can't really prevent the attacker from kind of, let's say, corrupting certain parts of the boot process, because then your machine won't boot anymore, and I'm not willing to make your desktop environment unbootable, but I will make it tamper evident. I will make it very clear that this machine has been tampered with, so that you as a user will know, and I'll also make it clear with your credentials. I'll essentially poison your credentials in such a way that an authenticating party knows your machine has been tampered, right? And this goes into the whole conditional access, zero trust policies, where, yep, you've got the right password and you're trying to authenticate with Active Directory, but Active Directory is saying, yeah, but your box is compromised, so I don't trust your password, right? Or you're trying to access a network resource or SMB, and the SMB service says, nope, you can't access that file share. I know your computer's been compromised. So by essentially storing secrets in ways that tamper evidence can corrupt or destroy those secrets, we can make it evident that something's gone wrong with the machine. Pluton is a Microsoft technology where they've embedded their own TPM inside of AMD's systems on chip, inside of Qualcomm's ARM system on chip, and in future Intel system on chips as well. This now gives you a secure coprocessor that's Microsoft owned that lets them store secrets as well as run certain cryptographic operations there, similar in a little bit to the secure element that you have, for example, on iOS devices, or Trust Zone that you kind of, or Samsung Knox, but it's owned by Microsoft, so it kind of lets them own the signing keys and integrate with the OS. And the final set of protections are all around memory, right? There's a number of attacks where external devices can corrupt your memory, and now we have IOMMUs that can prevent that, as well as virtualization scenarios where a physical user of the machine could compromise virtual machine state or steal virtual machine secrets. And we have technology such as AMD's SEV-SNP, Intel's TME, total memory encryption, where RAM can actually be encrypted now with keys that are owned by virtual machines, so that even though the host operating system and the host infrastructure provider doesn't have access to the memory that's inside of the VM, and even if they're physically tapping the bus and physically analyzing the bits on your stick of RAM, they only see encrypted data, right? So this shields you against hardware attacks, this shields you against physical attacks. And again, it means that even if someone does have physical access to the computer, it's still your computer. It could even mean that if someone has physical access to your computer, your VM is protected from whoever has physical access to your computer, right? And these are all innovations really in the last 5 years. And we always talk about how SKUs are getting better and better and better. A lot of this has happened in the last 5 to 7 years. So it really is, almost an exponential curve in terms of how much more secure systems are getting. And the industry is also reacting to that in new fundamental ways as well. For me, one of the most kind of exciting and interesting technologies that's being worked on is called Cherry. Now, Cherry is a fundamental rewrite of hardware architecture for the first time since von Neumann machines, essentially, where instead of having a processor that accesses memory by using pointers, 64-bit pointer, go here or go there, you're now accessing memory through 128-bit references, through contracts, essentially, that describe the byte or word or double word you want to access it, where you'll be accessing it from, why you'll be accessing it, what type of access will you be doing, and so you're essentially coding references that are signed and describe the reference you're making. You're not just touching pointers and hoping you're doing the right thing. And in a Cherry environment, memory exploitation almost becomes impossible, right? Nothing is fully impossible, but it becomes really, really hard to get a computer program to access memory in a way that it's not meant to, because every memory access is essentially a signed description of the memory access itself. Combine that with Rust, and you have almost, I'd say, the death of memory corruption. Now, Cherry still today is a 25 to 30% performance decrease in the software execution, right? So you run a program on a Cherry system, and there are some that you can buy. There's ARM Morello boards, and there's FreeBSD builds for Cherry. Linux is supposed to have a Cherry build by the end of the year, and you run the same software on a Cherry board or non-Cherry board, and you'll see on average 30% performance decrease. Sometimes 50, sometimes only 10. That's still too much, right? The industry is willing to accept a security feature with maybe a 1% security performance decrease. A 30% performance decrease we're not ready for yet, right? And I think Microsoft and other vendors are asking themselves, is there a future where this is a 5% performance decrease? Are we okay with 5? Certainly 30, at least for general purpose computing, isn't. Now, there might be other types of systems where the owner of that system says, I'm willing to pay a 30% performance penalty in exchange for the software that's running on this to essentially be, unexploitable through memory corruption. Maybe some systems, would be willing to do that, like a gaming machine in the Las Vegas casino might want to run on Cherry. We're not quite there yet. ARM64 is another interesting one, right? Apple, very famously, I think, over its history, has kind of shifted computing architectures and kind of made certain CPU manufacturers win over others, right? Apple famously used PowerPC for a long, long time. Then Apple pretty much killed PowerPC by going to Intel. And I'm not saying they're going to kill Intel, but they certainly caused a lot of pain for Intel by moving to ARM64 and their M1, M2, and future M3 processors. Windows also runs on ARM64. Now, unfortunately, Microsoft did with ARM64 what they did with the Zune, what they did with Windows Vista. And one thing that Microsoft is really bad at is knowing when something is ready versus rushing, right? The Zune 3, and for the youngsters among you, that was an MP3 player when we had MP3s and iPods. The Zune 3 is one of the world's best MP3 players. Unfortunately, the Zune 1 and Zune 2 were such horrible pieces of garbage that nobody bothered to buy a Zune anymore when Zune 3 came out, and Microsoft just gave up on the MP3 player business, and the market moved on. They did the same mistake with phones. They did the same mistakes with ARM. The first Windows on ARM system, which is called Windows RT and Surface RT, you could run 4 applications on that. I jokingly say it's the world's most secure Windows tablet because you can only run 4 things on it, right? And I had a Surface RT. I really believed in it. I even converted some of my training class materials to talk about Windows on ARM. It was just slow. You couldn't even domain join it. Like just nothing worked on it. Then they came with Surface RT2 and Windows RT 8.1, which I think you can run 8 applications on it now instead of 4. And they managed to port half of Office, but not macros, and macros around the world. And I think you could domain join, but only on some domains. So still garbage. Then they eventually said, all right, that was a mistake. Now we have ARM64, though, and we'll have Windows for ARM64, and you can run all your 32-bit applications on it. But it's 2018. Who still has 32-bit applications? Yeah, there's a few out there, and you can still get Office 32-bit, you can still get Chrome 32-bit, Visual Studio 32-bit, but a large majority of applications now are 64-bit only. Nobody makes 32-bit applications anymore. And there's still a bunch of things you can do on it, right? So by then, people are like, all right, Windows on ARM, that's a joke. I'm not going to look into that. Now, I'm sitting here today telling you that if you buy a Windows 11 ARM64 laptop or desktop, they actually have ARM64 desktops as well, you're going to have an incredible experience because they created something called ARM64 EC that essentially lets them run x64 code at almost native compatibility. They spent a whole bunch of billions of dollars on a whole hybrid recompilation JIT system that with some kernel magic and some compiler magic and a whole bunch of other computer science magic lets you run 64-bit unmodified apps, x64 apps, Intel apps on ARM64 with no issues. They ported OpenGL, they ported .NET, they ported Edge, they ported Office, and it runs everything. The only thing it doesn't run is 64-bit x64 drivers, right? You can have IS, you can have Hyper-V, you can have SharePoint, you can have Exchange, and these things run a day without charging your battery. And 99% of the exploits don't work on them because no one's writing ARM64 Windows exploits, right? So it's a great little system, and I wish Microsoft would invest even more, but they might have missed the window. I don't know if they have or haven't, but most people are sitting there, ARM64 Windows, what? Because for 10 years, they produced garbage there. But maybe there'll be a change. The other big industry change that we're seeing is around software supply chain, right? That's especially after SolarWinds and Log.js. Everyone's talking about that. The SBOM, the software bill of materials. That's kind of going to matter over time, I think. You're going to see certain types of attacks and certain types that get harder and get discovered easier. And of course, this whole idea toward moving more and more computation toward the cloud, right? I've seen ideas and demos of, for example, cloud-based rendering for games, right? Google had Stavia, where the game was on their servers. You also have web browser technologies now that are moving to a world where the web page actually gets rendered in the cloud. So even if there is an exploit or vulnerability in the way the DOM gets processed, it's happening on some transitive VM in the cloud, and it's not actually affecting your machine. So the world is moving towards increased sandboxing of stuff that's running on your machine and increased execution of stuff on other people's machines. So that will make security for all platforms safer over time. Outside of kind of technological changes, the other thing that's increasing security within Microsoft specifically is that they've learned some lessons. I gave a keynote at a French conference called STIC about, I think, 4 years ago now, where I was talking about my experience with the Microsoft vulnerability program, and especially the bug bounty program, where you'd submit a bug to Microsoft and get some money back. I've never been kind of a black hat vulnerability researcher. I've never sold to foreign governments or black market. I've always reported it, to Microsoft. And when they had a bug bounty program, I said, cool, now I can report and make some money too. And one of the things that fascinated me is I would report a bug in a function where the function did something that it shouldn't do. And they'd say, yep, thanks for finding the bug. Here's, at the time the bug bounty payouts were pretty nice. Here's $10,000. Thank you very much. And then the patch would come out. And then that function would fix the one instance where I pointed out that it does the wrong thing. But 8 lines lower, where it was doing the same wrong thing again, it was still doing the wrong thing. And then I tell Microsoft, well, you didn't patch it completely. I'd say, yeah, but you only told us here. You didn't tell us here too. But you guys have source code. Look at what I sent you and see if it happens anywhere else. It's like, well, it's your responsibility to tell us if it happens anywhere else. Like, are you going to pay me for everywhere else I pointed to? Like, well, yeah, that's a new bug report. I'm like, okay, it happens here too. $10,000, thank you. Patch comes out. And here, thank you very much. $10,000, right? And also here, thank you very much. So I made a presentation how I ended up buying. I'm a huge fan of the Japanese Toto toilets that they have in Japan. And I wanted those for my house in Seattle. And I have 4 bathrooms, 3 full and one half. So I managed to get enough bug bounties in the same Windows function with the same bug that I managed to buy 4 Toto toilets, totaling $48,000 US. And I talked on stage about this, and thank you, Microsoft, for making wiping my butt so much easier with $40,000 of money that you could have probably spent on something better than cutting me checks for the same vulnerability in 4 little locations, right? I said, you need to do better. You're the world's 2nd largest operating system vendor. Please do better. Like, I don't mind the money, but seriously, this is ridiculous. And I don't know if it was because of that presentation. I'm not going to be arrogant enough to say I changed the world. I know it made its way to executives, and the toilet analogy really helped. But a few months later, they create Morse, right? And Morse is a team in Microsoft that stands for Microsoft Operational Offensive Research Security Engineering, something like that, I believe. And they do an amazing job now of finding variants. When you submit to Microsoft a bug now, for the first time in decades, they will look for variants. They'll write a fuzzer that tries to find more examples of what you've done. They'll use code QL and write a rule to see if what you've reported happens in other places, in other products. And they have a red team internally that tries to find bugs as well. And Morse has done a phenomenal job. If you look at most MSRC patches now, I'd say a quarter, if not more. If you look at the acknowledgements, you'll see Morse team, Morse team, Morse team, Morse team, Morse team. And you finally have the OS vendor finding bugs in their own operating system, which I think is a good thing, right? I've always been annoyed at Google Project Zero finding bugs in other people's products. I'm like, why don't you find bugs in your own first? So Microsoft now has a Google Project Zero team finding bugs in their code, which is a good thing. They also collaborate a lot more. They're working a lot more with the open source community. Microsoft now is a huge sponsor of Clang. Because of Clang, you can now compile with ASAN, which is the address sanitizer that Clang has. They've worked to implement Control Flow Guard and Control Flow Integrity in CastGuard in collaboration with Clang. Clang can now produce Microsoft public symbol files or PDB files. And they've also made ASAN work in the kernel. So they have something called KSAN. And now Microsoft Windows driver developers can leverage this kind of Linux open source client technology to find vulnerability in drivers as well. And they publish a lot more of their specs. They write a lot more blog posts about the technologies that they're doing and using. So they are becoming more open, and they have more interaction with the security community than they did before, which also makes things more secure. So kind of taking all this together, it looks like this is great, right? Security is solved, and if you run Windows 11, you'll all be fine. But my thesis, though, is that even though these are all great things, and I'm for all of them, I believe that in the next, let's say, 3 to 7 years, let's call it 5 on average, this will actually have a potentially unintended side effect that actually will lower security, right? So what I'm going to say, and I'll try to back up my thesis, is that we might see more Windows vulnerabilities and more security vulnerabilities in Windows for a little bit of time until we kind of get over a hump to kind of fully absorb this new world that I've talked about. So why is that? Well, so Microsoft has something they call a dog fooding culture, right? The idea of dog fooding in software is, eating your own dog food. So essentially trying your own beta software, trying your own things as you're building them. Now, Because of dogfooding, though, that means that your engineers are eating the very latest betas and internal versions. They're not trying necessarily what the world is running, right? So the world right now is still mostly running Windows 10. I don't know, maybe a third of the world is now Windows 11, probably less. What do Microsoft engineers run? They run Windows 11 23H2 in their office computers right now, right? The version of Windows 11 that's coming out next year that is in preview builds and that you can run as well, they're already running that. And they're running that in a domain with the latest and greatest, Azure AD mitigations. They're already, most of them, running in adminless mode. Windows Hello is enforced. So the average Microsoft software developer's view of what it's like to use Windows and on a Windows domain is heavily skewed toward enabling and turning on every single mitigation technology and capability that Microsoft has to offer on the latest and greatest hardware that Microsoft buys its developers. So it starts to feel like that's the rest of the world. That's what the rest of the world looks like as well. It also means that when you're writing code, right, because you're writing code in Rust, let's say, and you're using the latest C++ features and using a GSL and you're using the latest runtimes, all of the security guarantees that are being offered by the languages and the runtimes and the templates that you're using get you to write different code where you're thinking less about certain classes of issues because the runtime or the environment you're running is essentially making those non-issues. Like I'll give you a very simple example from my CrowdStrike days. In Windows, when you work with a resource, you have to open what's called a handle to it. So you want to work with a file, you open a file handle. You want to work with a mutex, you open a mutex handle. When you're done working with a resource, you close that handle. You call the close handle API to close the handle. Now, when we do code reviews and we saw people using handles in their functions, of course, our eyes would look for, are you closing that handle anywhere? Or if you're passing it to another function, is it closing the handle? What is the lifetime of the handle? In the same way you track the lifetime of memory allocation, right? Is the memory allocation freed at some point and is it not reused? Is the handle closed at some point and not reused? Well, with modern C++, though, you can have what's called RAII, right? Resource acquisition is initialization, where you can add scopes around resources, like unique pointers and smart pointers and shared pointers, and you can do that to other kinds of classes as well. So we came up with this great idea of taking the Windows handles and encapsulating them in what's called a scoped handle, such as that when you created or opened a handle to something, once your scope was run down, so once you were done using the handle, we automatically added essentially the structure for that scope that would close the handle. So if a function created a handle to something, by the time the function returned, the compiler would auto-generate code to close the handle, which is great because now you no longer have to think about closing the handle. The compiler will write the code for that. So people that started writing C++ 17 code at CrowdStrike, their code reviews would get held up because people would be, you forgot to close your handle over here. And the developer would say, no, remember we're using scoped handles now. The compiler automatically closed the handle for me. And slowly over time, developers stopped looking for, did you close your handle? Because like, oh yeah, scoped handle means the handle gets closed automatically. Scoped handle means the handle gets closed automatically. After 4 years of that, if I gave one of these developers standard C code that doesn't use templates and scoped handles and all that, and had them review a Windows function, do you think they would realize that that function did not close the handle? Probably not, because mentally, they're used to reviewing code where that's no longer something they have to worry about, right? It's handled automatically. And I'm not against automation. I'm not against templates. I'm not against compilers adding code. I think overall, you're going to get better, more secure code by automatically closing the handle. But it does mean that for our mindset, right, we're all humans, we're going to deprioritize our ability to find that kind of bug. And so back to the Microsoft example here, as they're running on the latest and greatest and writing the latest and greatest, right, their brains are going to be less tuned to finding bugs that are no longer necessarily exploitable under modern conditions, but could still be exploitable under current conditions. And the idea is as they're writing code for what they're running on, which is the latest and greatest modern system with the greatest and latest runtime, when that code runs on older legacy hardware, when that code runs on a Windows 10 system where the mitigations are turned off, are they realizing that that code is actually vulnerable on those systems? And number two, as people do find vulnerabilities on those types of systems, is Microsoft going to prioritize fixing those vulnerabilities? Or are they going to say, well, in a couple of years, that's not really going to be an issue anymore because this mitigation and that technology will make this impossible? So will they be writing more vulnerable code in some situations? I think so, because that code will be vulnerable but not exploitable on future systems. And will they be patching potentially less vulnerable vulnerabilities because in the long term, those vulnerabilities won't be exploitable? I also think so. And I have one piece of data to kind of back this up, which is in Windows 7, they killed a bug class called the null pointer dereference. A null pointer dereference means that you have a pointer to a memory location that's essentially 0, which is considered by programmers to be invalid. But in reality, both Mac and Linux and Windows allowed you through various tricks to allocate 0. So you could actually allocate the null pointer. That meant that whenever something thought it was accessing invalid memory and crashing, you could coerce it to actually touch valid memory that you controlled, and then through another level of in the reference, perhaps cause a read or write to happen in kernel memory, for example. Both Linux and Mac and Windows around the same time frame, around Windows 7, kind of made null pointer allocation impossible. They all added code in the memory manager to prevent allocating a null pointer. Because of that, if you now submit null pointer dereference bugs, Microsoft will likely not fix them or say, that's not a vulnerability, we don't care, or really deprioritize it, mark it as a denial of service attack, and maybe patch it in some future version of Windows. But they will typically not give you a CVE, and they will typically not issue a KB or a patch if your vulnerability is a null pointer deref. Even if it's a kernel null pointer deref, the only difference is if it's a hypervisor bug. Yes, if you find a Hyper-V null pointer deref where you could take down Netflix.com, they'll fix that. But a local DOS, they don't care about it anymore. But in Windows 10 Redstone 2, so that was about 3 years ago, they added something called virtualization-based security enclaves, VBS enclaves, which allow you to run code whose memory and logic is protected by the hypervisor in a similar way to Intel's SGX or ARM's Trust Zone. And as part of creating VBS enclave support, they made some tweaks to the memory manager. And while making those tweaks, they accidentally made it possible to allocate null memory again. And this is something Microsoft often does, and I think all large software vendors do, is they write something that's secure and that has a certain threat model. And over time, they add more and more features and more capabilities, but they don't go back to the threat model and look at how does that new feature affect these assumptions and these guarantees from 5 years ago, right? So they add a whole bunch of code to support a brand new security feature, enclaves, but by doing that, they break a Windows 7 mitigation. And for about 1.5 years, you could allocate the null pointer again until a Iranian, I believe, researcher found this out, submitted a bug to Microsoft, Microsoft patched it, but during that window, null pointers are allocatable again, meaning that all of those bugs that Microsoft hadn't patched because they're like, null pointer, who cares, that's impossible now, suddenly wasn't impossible anymore. And I'm not advocating that Microsoft should fix every bug or should, treat everything as priority 0, because I ran an engineering org. I understand the value of having prioritization. And sure, do I fix a design flaw vulnerability that's going to affect all versions of my OS, regardless of the hardware you're on? Or do I fix a memory corruption vulnerability that's not going to work on modern hardware? If I have to pick, I'm going to fix the design flaw. I'm not going to fix the memory corruption vulnerability. So my hypothesis here is over time, as Microsoft moves towards newer and newer features and mitigations and hardware systems, it's possible that if you're stuck running only Windows 10 and you only have an Intel 12th generation CPU, there might be some vulnerabilities that actually are exploitable on your system that might not be exploitable on a modern system. And Microsoft might not have the resources to fix all of those and say, well, you know what, you're choosing to stay on a 10-year-old system, you're going to pay the price, even though it's still supported. Right, so they have this interesting thing where your OS is still under support. Security patches are still going to be given to you, but they're not going to go and patch that vulnerability because it doesn't rise up to the level where it's necessary. I'm not saying this will happen en masse, but it's something that we might start seeing. The other thing that we might start seeing, though, is vulnerability researchers who are seeing this presentation and are seeing the reality of what's happening might say, well, crap. all these bugs that I've got that are exploitable today, they're not going to be exploitable 3 years from now. So let me dump them now. Let's get the bug bounties now. Let's weaponize them now. Let's sell them now, because my window for making this a usable bug is shrinking and shrinking and shrinking. And so here's 3 CVEs this year alone. They're actually really, really, I'd say, simple bugs. They're not very complicated. And I'm not going to go into Windows internals of everything here, but it's things like it's missing one line of code when you're calling it from user mode to make sure the buffer access is safe. Or it's not even checking if you're coming from user mode or not. Or it's casting something without checking if it's casting the right thing. I mean, it's object type confusion and missing one-line validation checks. Interestingly, it's all bugs that have been there since Windows NT 4. One of these bugs is in a component called afd.sys, which stands for, I kid you not, another fucking driver, which is written by the sockets team in the Windows NT 4 timeframe. The other one is a Microsoft kernel streaming driver, written to support cameras for Windows NT 4 as well. Why is it that in 2023, these one-line bugs, not super complicated things, suddenly start getting dumped? Is it because researchers are saying, well, these things won't be usable anymore? And none of these bugs actually, once Microsoft enables what's called SMAP, or Supervised Remote Access Protection, once 23H2 ships with the KSLR info leaks, and once HLAT comes out in the new Windows version next year, these 3 vulnerabilities, the way they were exploited, at least by the researchers, the exploits won't work anymore. Now, will there be other ways of exploiting the vulnerabilities? Maybe, but all these 3 would be patched by next year's computers and next year's Windows. Not patched, but essentially unexploitable by next year's computers and by next year's Windows versions. So I do think we're starting to see researchers pick up on this and kind of liberate some bugs now, so they can get their CV, so they can get their bug bounties, so they can get their blog posts and the security conference talks, which is something that motivates a lot of us. The other thing, though, is that as those classes of vulnerabilities get kind of closed, as it gets harder and harder to go after memory corruption vulnerabilities and to go after some of the other stuff I've talked about, I think you're going to see an increase in other types of research. Since I've been doing VR, I've always talked about how I'm personally never been interested in memory corruption. I've always been interested in design flaw and logic bugs. Those are a lot more fun to me because those usually involve code that is a lot harder to patch, right? Like the entire architecture of this thing is meant to be vulnerable. Well, how do you patch that, right? And so they're harder to fix. They're also harder to find, but they usually persist for a lot longer time as well. So I've always been a bigger fan of design flaw and logic bugs because you'll never have a design flaw guard, right, implemented. So I think you're going to see more and more researchers looking after those types of bugs. The other thing we're already seeing is a lot more cloud-based attacks where we're really going after tokens, right? So forget credentials and how they're stored, forget memory corruption and memory safety and all that. Ultimately, as stuff is moving to the cloud and things are being, APIs are checking for tokens, token forging, token minting, token stealing, right? All these token-based attacks, which are not very well understood by the vast majority of security researchers, including myself. Like, I don't really get the cloud too much. And when people talk to me about how this AAD token was forged into an MSA token by stealing the signing key for the other tenant in the forest, I'm like, tenants in forest? What are you talking about? But this is how a lot of modern attacks are happening now. And nation states are stealing emails by forging tokens, not by getting code execution. Now, I mentioned how platforms are getting more secure, but it doesn't necessarily mean that third-party services and third-party applications are getting more secure. Right, there's lots of stuff that we run on our boxes, some written by Microsoft, some not written by Microsoft, that hasn't necessarily had the same level of security development lifecycle or SDL put into it, right? So your third-party, AV vendors, your third-party games, your anti-cheat, or even Microsoft's own services, right? SharePoint, Exchange, IIS, they're not necessarily getting the same level of attention and raising the bar in much the same way. Now, some of these services are going to be moving toward cloud, right? And so it'll be theoretically harder to attack Exchange Online than an on-prem Exchange server. But back to number 3 here, back to cloud token theft, it'll be harder from like a memory corruption perspective, but there's other kinds of cloud-specific attacks that could attack Exchange Online that maybe won't work with your local on-prem Exchange server. And again, some evidence around this as well. If we, I mentioned MSA AED tokens. So the Storm 558, the Azure breach, where Microsoft, pointed out that they were attacked by what they classified as China, I believe, where the attacker found an expired signature. And Microsoft wasn't checking, their own code wasn't checking if signatures were expired or not. Using an expired signature, they signed one type of token that's meant to be used for consumer MSA accounts, but you could actually use it for Azure AD accounts. And then an API that's meant to allow Azure AD and MSA tokens also lets you use it to issue Exchange tokens. And according to Wiz, other types of tokens as well, but Microsoft said, no, only Exchange was used. And basically by combining a design flaw in not checking signature validation, a design flaw in allowing an API to issue tokens for services it wasn't meant to be used for, and somehow the signature getting stolen in the first place, these attackers are able to download emails off, US and other countries' unclassified email servers without kind of any vulnerability, classical vulnerability, other than theft and design flaw logics. Also, if you look at like a September patch Tuesday, right? So this is last month's data. I'll show you October as well. NTLM issue in Word, RCE in Internet Connection Sharing, RCE in Visual Studio, RCEs in Exchange, Prevesk in SharePoint, RCE and Prevesk in Azure DevOps Server. The vast majority of vulnerabilities were not in the Microsoft kernel or the Microsoft drivers. They were in third-party services, and the large majority of them are actually RCEs. So if I look at here, let's see if I can zoom in a little bit. I guess not, but 45 RCEs in October, right? Which is almost about half of the vulnerabilities were RCEs. And here, if you look at just, I know you're far away, but it's .NET Core, .NET Framework, Visual Studio, 3D Builder, 3D Viewer, Azure DevOps, Azure HD Insights, Azure Kubernetes, Dynamics Finance, Exchange Server, Identity Linux Broker, Office. Like I only did the first, this was like had 30 items. I picked the first 25. Windows kernel, Windows platform is like at the bottom. It had like 2 vulnerabilities, right? So the vast majority of vulnerabilities we are seeing today are actually third parties and are actually RCEs, right? Because we're kind of moving away from the classical security research. At least that's my hypothesis, right? That's my thesis. We'll see the data continues to show this. I might be wrong, but point of a keynote is to be a little bit spicy and get people to agree or disagree and discuss on things. So to kind of summarize, security is getting a lot better. Exploitation is getting a lot harder. Because of that, we might see a little window of people dumping bugs, of Microsoft not necessarily prioritizing things that won't be bugs in the future. And we're definitely going to see attackers shifting their mindset away from memory corruption and kind of traditional exploitation to doing more cloud-based work, to attacking more third-party services, and kind of going away from attacking the platform, right? Until the next shift, right? It's always a cycle, and attackers will always find the next thing that's the next most vulnerable thing to go after in this cycle. So with that being said, thank you for having me, and we'll open it up to any questions. Thank you.
If there is nobody, okay.
Over there. I don't have a copy of Windows internals to give out. They're too heavy.
Hi, Alex. Thanks for the great presentation. So my question is, like, if the operating system and hardware working together will come close to, let's say, perfect, what's the future of like EDR, XDR tools such as CrowdStrike?
Sure. My personal belief has always been that EDR, XDR tools shouldn't have to exist, right? I think the OS vendors did humanity a great disservice by essentially, making programs execute as quickly and as efficiently and as easily as possible in our systems without reading papers written in the 60s and 70s about how to properly secure architecture. Now, we might not have had the innovative world we live in if they hadn't done that, sure, but I think they've made conscious choices to reduce security, which created the market for AV and for EDR and for all these things. In a perfect world where the OS platform enforces all these things, there's a lot less need for third-party EDR, XDR, because those attacks are impossible. What you still do need is logging and auditing, right? But even the OS could provide that. So I certainly think that, I make an analogy of if car manufacturers would make cars without seatbelts, and the very next thing after you buy a car is you go to seatbelt industry, seatbelt hat, and you try to find which seatbelt to buy for your car. That's kind of the world we live in today, right? And I wish it wasn't so.
Not sure. Yeah, here we are. You're saying that the developers in Microsoft have sort of lived in an ivory tower for some time and still live there because they're using the latest and greatest, and then we have the third-party applications or the sort of the service applications running on top of the OS, and still we have the regular user. So are we widening the gap now between the regular users and the developers, and what is defined as secure and neglecting user behavior?
So I do think we're widening the gap in some scenarios. Things like moving to biometrics and passwordless do try to kind of alleviate some of that by taking into consideration user behavior. But I do think back to Miko's Nokia example. I do see a lot less thought going into how is the user going to respond to this? How does the dialogue look like when smart app control doesn't let the thing run? So in a way, we are widening it. We're then making what's protected by the tower better and more secure, and so we're minimizing the impact of the widening, I guess, is the theory, but making it wider. So TBD if that proves out to have massive issues in the future or not. But the user behavior is still, I feel, being ignored when it shouldn't. Yes, that's a good word for it.
So I have one question from my development background. So you are saying we are moving security features into the platform and into the hardware, and as a result of that, we are streaming into the future where developers will develop more buggy and more sloppy code. How to handle those situations?
Yeah, so developers are going to be writing, let's say, more buggy, more sloppy code. It'll be okay because the code will be sandboxed and written between a few things. How do you react to that? Well, one thing, and I don't have the answer, but one thing to think about is, should we react to that? As in, yes, for the next 5 years, while not everybody has a sandbox, the sloppy code is a problem. But if we make code writing really easy, and 5 years from now, it doesn't matter if the code is sloppy, right? How do you convince an engineering org that they should focus on making sure developers write proper code when the improprieties don't really matter? Like, I think it's going to be a hard economic, like capitalistic argument to say, yes, the code is sloppy, but it doesn't matter, but it shouldn't be sloppy anyway, right? That's what I fear. So that goes back into user experience, right? So I think we need to make it not about is the code secure or not, but what is the user experience like, right? And a lot of developers that are not Microsoft actually don't end up using their software, right? Like at CrowdStrike, most of the kernel developers had never logged into the UI, right? To actually see how the ETW event and the filter driver makes its way there. And in many cases, maybe they didn't need to, but in some cases, I think would have helped understand. We had a case once where a kernel pointer was making its way to the cloud, right? Not within a thread model, that's fine, but why does the SOC admin need to see the kernel pointer of the file, right? It's not relevant in the UI. So I think more UI dogfooding, more user experience-based dogfooding will help with that. And you do really need like good, when I ran the engineering team, one of the things that I realized is there's not a lot of good onboarding on how to start developing for a company. Every company has their own framework, their own way of doing things. And oftentimes the programmers end up in this cabal where it's kind of like a lot of hazing, a lot of you better learn our way, and not a lot of kind of internal growth and training. And I think companies could also benefit from that. Maybe one last one if there's time. Otherwise, everyone's hungry. All right. Thank you very much.